Hello, today I would like to share this paper, Learning to Communicate with Deep Multi-Engine Reinforcement Learning. It's an old paper posted in DIPS 2016, but it's very popular in multi-engine reinforcement learning domain and is one of the pioneering works in multi-engine communication. The idea is simple but inspiring for my current research. I will share this paper in 4 steps. First is the background. The problem of this study is very straightforward. If a task requires information sharing to solve, how can a team of engines learn the communication in order to solve it when no prior protocol is produced? In other words, the engines need to communicate to achieve a task, just like what our human beings do during cooperation. To this end, they are the first to answer the following questions. How can engines discover the communication protocols that they need to coordinate their behavior? How to achieve the communication learning in the context of deep learning? And to some extent of philosophy, what are the insights from the outcome of engines learning to communicate? And before we dive, what they are studying is about learning the ability and the emergency of languages among AI engines. And before we dive into their method, let's have a quick review of the classical reinforcement learning problems. The reinforcement learning trains engines to solve a sequential decision problem through trial and error in the environment. And just like this minion tries to find a banana in a maze, it needs to determine the moving step in each time step to achieve the goal. And here the engine is the minion and the control action is the moving step, and the goal is to obtain the banana. Specifically, at each discrete time step, the minion will observe the state of the environment just like where it is right now, currently. And then it will determine a moving step according to the state, and after that it will receive a reward from the environment. Maybe it indicates how close he is the distance. Maybe measures the distance between the minion and the banana. So in this way, the action can be evaluated, and once the sequence of decisions is evaluated, the process of the minion can be trained. Essentially, during training, we are approximating the value of each state action pair, and then given a state, we can select the action with the maximum state action value. So what reinforcement learning does is actually to approximate the value of each state action pair of a policy. Mathematically, here is what we want to approximate it. Here is the station value which we want. We also call it the Q value. And we usually approximate it by a Bellman equation. In other words, it's based on the current state action value is determined by the current reward and the future return after this state action. And for the Q learning, the optimal state action value is the greedy policy at each time step. So we want to approximate the Q value for the greedy policy when we use Q learning to solve the task. And when it comes to high-dimensional and continuous state space, we usually adopt deep neural network as an approximator for the Q value. We usually maintain 2 neural networks for the DQN. The first is the evaluation network, which we will learn the Q value continuously, and the other is the target network, which is used for the bootstrapping. It will update periodically with the parameters of the evaluation network. And there actually has 2 steps. If an engine arrives state X, he will select the action based on this network and this action and this state will correspond to this Q value, and this Q value is the neural network wants to approximate, and the true Q value of this one is approximated by the immediate reward from the environment and an approximated term from the target network, the maximum Q value at next step. And with the true value and approximated value, we can formulate a mean square loss function to train the neural network. It's very straightforward, just like the traditional supervised learning process. And we only introduce the basic idea of DQN here and omit some tricks such as the experience replayed. And DQN actually is the backbone of this study. The authors proposed two architectures on top of DQN to learn the communication among engines. The first is called the reinforced inter-engine learning. Exacting is very straightforward. The engines implement the communication like other actions based on the Q value. So in this framework, they actually maintain two kinds of Q network. The first is to approximate the Q value of action. The second is to approximate the Q value of a message. In addition, the second one is called differentiable interaction learning. The key novelty here is that they formulate a trainable output in addition to the Q value for each engine. Just like the procedure here, the trainable output of engine 1 is passed to the following engine 2 as a message, where the engine 2 calculates its Q value. In this way, the loss gradient of engine 2 can broadcast to the trained engine 1. And so it's also very straightforward, but I think it makes a lot of sense. In this way, these two engines are related by the gradient. And they propose a channel regulator for the training phase and execution phase respectively. You may think it's very simple regulator, but it makes a difference. We can also learn that the reinforcement learning is more about theory work, but it requires much critical implementation tricks. This is one of the tricks in this framework. They also extend the DQN with recurrent neural network structure. In this way, they can consider multiple historical time steps when approximating the Q value at current time step. Such setting will alleviate the stationary issue of multi-engine reinforcement learning. In this architecture, each engine will consist of an IN for T time steps, where T is the length of decision sequence. And the state embedding of this Q network is produced by element-wise summation of observation, message, and action of last step. And the authors designed dedicatedly two games to study their framework to identify the significance of the communication among engines. The first game is called Speech Riddle. It's a very well-known riddle described in a formal report. And here is what this riddle does. 100 prisoners have been duly ushered into prison, and the warden tells them that starting tomorrow, each of them will be placed in an isolated cell, unable to communicate among each other in this cell. And each day, the warden will choose one of the prisoners uniformly at random with replacement and place him in a central interrogation room containing only a light bulb with a toggle switch. The prisoner will be able to observe the current state of the light bulb. If he wishes, he can toggle the light bulb. He also has the option of announcing that he believes all prisoners have visited the interrogation room at some point in time. If this announcement is true, then all prisoners are set free. but is false, all prisoners are executed. So this is a problem that requires cooperation, and we can formulate in more simple word. Each day, when a random prisoner is asked to the interrogation room, he will check the position of the switch. That is the message from the last prisoner in the interrogation room. And then he will determine whether all prisoners will have been interrogation room at least once or not. And he can also send message just by deciding current position of the switch. Since each prisoner is isolated and the only information they can share is the switch of the interrogation room, so they have to find a communication protocol to use this information. Otherwise, they had to take chance for freedom to answer to determine whether all prisoners have been interrogation room by chance. And here is one example of communication protocol to solve this task. The first prisoner selected is in charge of turning the light on whenever it's fouled off. Each other prisoner is to turn the light off at the very first time they find it on. Otherwise, they have to leave it in the state they found it. When the first prisoner selected turns the light on for the nth time, they can safely assume that all prisoners have been in the interrogation room. So this is one of the example communication protocol for this task. And this study formulates the reinforcement learning in 4 parts. The first is the observation of the engine. It is 0 or 1 to indicate whether the prisoner is in the interrogation room or not. And the action is none or tell. None indicates that the prisoner will not determine that all prisoners have been to the interrogation room, and tell means that the prisoner announced that all prisoners have been at the interrogation room. And the reward is plus 1 if the announcement is correct, is -1 if the announcement is false, and 0 for no announcement. And here the message is available only if the engine is in the interrogation room, and this message is formulated as the position of the switch. The prisoner in the interrogation room can first observe the position of the switch, and then they can determine the position of the switch. And these two processes is the receive message and the send message. And you can maybe you regard this problem as a very simple problem because the median here, but actually the policy space in each step is very large. It can reach to the 4 to the power of 3, and if you consider t historical steps to make a decision, then it will be the 3 to the power of t of the exponential. So it's a very large policy space. And if you consider the t time steps in a sequential decision control problem, it will be much larger. So actually it's a very complicated problem, and it requires communication. And here's the experimental results. From the comparison of the reward, we can see that the model with differential communication is the best, and the model with communication is better than the ones without communication. And one point that should be noted that the parameter sharing is also beneficial in the communication learning. And they also studied the game based on a classical meaning data set. The first is the multi-step meaning data set. This task is to guess the digit value received by other engine by communication. The decision steps is 5, and the state here is the pixel values of an example of the means for each engine, and the action is the digit value from 0 to 9 of the other engine. And the reward is the points, and the reward is 0.5 for each correct guess, and if 2 engines all answer correctly, that they will reach the maximum reward 1. And since that each engine will do not observe the state of other engines, he will not know what other engines receive. So they need to send a message to let other engines know what you observe. So the message is a one bit coding to indicate the other engine what I'm observing in this task. And the second task is a little bit complicated. It's a color digit mixed. The 2 engines have to first select which to guess and then guessed. So basically, they have to determine to guess whether their color index is equal to the priority of the other engine's digit, or guessed whether their color index is equal to the priority of the other engine's color index. After select one of the 2 tasks, it will guessed. And the state here is the pixel values of the example. And in this time, the pixel value is in a randomly chosen color. And the action is the binary action. It's 1 for true and 0 for false. And the reward is different for different tasks. If you select the first task and you achieve, you can get reward 2. But if you select the task 2 and you achieve, you only get the reward 1. So basically, the engines have to find a good task and then achieve in this task. So the message here is to communicate which task to choose in other engines and what the other engines observe. So in this way, it requires a much more complicated communication. And here is the experimental results. The reward comparison again indicates that the differentiable communication framework behaves the best. And one interesting point is that the message encoding for each true digit is unique, and therefore the message does not provide ambiguous information. So the message makes sense for this task. For example, if the true digit is 1, the message is each time step is this. But if the true digit is 0, the message in each time step is this. So these 2 messages are totally different. So the engine can observe this message to determine determine its guess. And finally, they emphasize the function of the regularizer in their framework and find some insights of the communication. In a speech reader game, adding noise during training can result in 2 different modes. And in this way, it makes sense for discrete size in testing, because you have 2 peak. Then when you do the discretization, you have 0, 1, 0, just like this. But if you if you have only 1 mode, it makes no sense to discretize the message. Interestingly, the language of human being is also discrete, so they find some similarity of the language in the engine and human being. So the summary of this paper is that the key of engine communication is to derive a good communication protocol, and we can learn communication protocol directly from inter-engine gradient. And also the parameter sharing can also accelerate learning in communication tasks. Thank you for your attention. Oh, my throat.